Alright, let's continue our discussion regarding this flexural members. Now, in the last video, we talked about the internal forces for flexural members, and right now we are moving on to the geometric properties. Although we have already done this in our first lecture regarding the geometric properties about area, we mentioned about area, we mentioned about the polar moment of inertia and inertia as well. But I just would like to have some review here. So let's write here moment of inertia, and the symbol that we use for the moment of inertia is I, and there's a subscript right here because that depends upon which axis are we going to rotate the area. Is it in the x-axis or is it in the y-axis? Okay, so what this means is that, for example, I have this I shape member, and this is in flexure, and let's say this is my x-axis and this is my y-axis. Okay, so what that means is that if I'm going to rotate the area along the x-axis, then it's gonna be something like this. Okay, so that's the this is my x-axis and this is my y. Okay, and when we say rotation about the y-axis, then that means it's gonna be something like this. Okay, so that's the y-axis. Okay, and um, for for shapes that are not equal in dimensions and for non-equal area distribution, then there's going to be difference in terms of the value of ix and iy. Like for example, this one, if you bend, or let me draw a simple one. I think we can understand this. Let's say we have this rectangular area and compare this to the area, I mean same dimensions, except that this one is rotated in this axis and this one is rotated in uh, this axis. Okay, so if we say this is our y, so this will be our y and this will be our x, right? So that means that there's gonna be a difference in the resistance if we bend it in this manner as compared it to you bend it in this position. And the answer for that, or the explanation, is that if you have much more area away from the neutral axis or away from the axis, let's say this one away from this axis, then there's much more resistance. So if you have less area like this, there's not much area away from the axis, then there's I mean it's gonna be less in resistance. Okay, now different shapes will have different equations or values for the moment of inertia, and in our lecture handouts we have here some selected shapes, like for example rectangle, which is typical common, and circle, and as well as triangle. So here we have ix is equal to 1 over 12 bh cube. Just take note that this ix refers to the axis where it passes the centroid. Okay, so ix is equal to 1 over 12 bh cube. Now here's our height and here's our base. And in terms of iy, actually if you rotate it along the y direction, then your base actually becomes the height, and this one, this base becomes the height and I noticed some typos here, so this must be just letter B. Okay, so here's our equation, and for a solid circle, we just have the same ix equal to iy, which is just pi over 4 r cubed, or in terms of its equivalent in terms of expressed in terms of diameter. Now another parameter that's also typical in flexural members is the s, and that's what we call the section modulus. And the relationship of section modulus to the moment of inertia is given by this equation. So s is equal to I all over c. Okay, if this is length to the fourth, and this is length to the to the to the one, then the unit of this would be length to the third. So for example, millimeter cube. Now the c right here is actually that's the distance from the neutral axis. So if, here's our centroid and here's our neutral axis. So that's the distance from this to the any other. I mean, it could be the outermost fiber or outermost plane, or it could be other location where we want. Like for example, we want this point. We want to evaluate the stresses at this point. Then that's gonna be our C. And that's why in some references or in some lectures you would notice that instead of C they use actually the symbol Y, because C denotes the distance from the neutral axis to the outermost fiber. But um, for us here it's just symbols, and we just have to really understand what this means in terms of let's say it just means the distance from the centroid to the point of consideration. So it could be this point, or it could be this point, or whatever point. Okay, so if it's just a distance, it's just meter raised to 1. So this one, the section modulus is um, length to the 3. Now there are also equations for basic shapes. Like for example, rectangle, we have s is equal to 1 over 6 times b times h squared. Okay, so you just have to refer to the table, but just take note that this equations right here, they just mean that um, the axis of rotation passes through the centroid. Now, what happens if the axis of rotation is not at the centroid? Then that means, like here, for example, so instead of, I mean, supposedly the axis of rotation should pass right here. But what if I want to rotate this area? I want to rotate this area in this axis, right? So I want this axis. So that's away from the far away from the centroid, and if that's the case, then that's gonna be um, I mean, we have to use the parallel axis theorem. Theorem just states that the I think it's the moment of inertia. I mean, the total moment of inertia is just simply the moment of inertia that passes through the centroid. So it could be x or y plus the area times the distance from the new axis to the centroid. So that could be ay squared or sometimes ad squared. So again, it's just symbols, but you have to understand the concepts behind. So that's the distance from this to that. So we have this ix, um, that's the moment of inertia that passes through the centroid. Okay. Also, for some regular shapes, so at the back of the textbooks, there are geometric properties of structural steel shapes. Like for example, here we have it says here a wide flange section or a W-shaped section. So when I say W shape wide flange, it's this shape. And you would notice here that there are a lot of designations. It's tabulated, and for example, we have a W section that's 610 by 140, and this 610 I think denotes the depth. So that's the approximate depth. So you would see here depth 617, but this one is 610. So there's some difference in the root or in the fillet right here and the thickness. And this one denotes the, I think this is the kilogram per meter length. But the point right here is that there are data for, let's say, I sub x. So, for example, I sub x in terms of mm to the fourth. If you rotate this along the x-axis, we have a moment of inertia of 1,120, and take note times 10 to the 6. And for the section modulus, there's also a section modulus right here. This is 3,640 times 10 to the 3, and that's in mm cube. And another one right here, this is the radius of gyration, and I think I have mentioned this in our lecture number 1. It's just simply um, some way of representing the moment of inertia, but in terms of length. Okay, so that's it. That's the radius of gyration. And in terms of mm, this is 251. Now, you see here that the values for the x-axis are different from the y-axis. Okay, so later on we'll have a problem wherein we are going to use this table to select which shape are we going to use for our problem. Okay, so that's all I think, and there are also C shapes and hollow structural sections, or HSS shapes. Okay, and what else? We have also many others. Okay, so now let's move on to the bending stress. Okay, so if we have this beam right here, let's say we have a simply supported beam and it's being loaded, let's say some arbitrary loading, and if we cut a section, or once it's loaded, there's gonna be a deformed shape. Once it's loaded, there's gonna be a deformed shape like this. So from this original shape, it's gonna deform this way. But why is it deforming? It's just simply because of the stresses. So if you cut a section right here, if you cut a section, what we see, actually sometimes in terms of stresses, it can be drawn just straight, but this one I think I just want to emphasize the bending. Okay, so once you cut a section, then you notice or we know that there's gonna be bending moment, right, and shear. Right, so we have bending moments right here, and we have a shear. Now this bending moment, actually, for now we'll focus on the bending moment. So this bending moment produces bending stress, and the bending stress distribution would be something like this. There's gonna be a neutral axis right here. Let's say this is NA, that's the neutral axis, and at the top or above the neutral axis, there's going to be compression. So you notice right here that it's actually a shortening, so there's going to be compression forces. But at the bottom, at the bottom of the neutral axis, there's going to be elongation, so there's got to be tensile forces. Okay, so if there's tensile and compressive forces, then we can express this forces in terms of stresses because we have the area. So it would be something like this. So here's our stress distribution. At at the top, there's gonna be compression forces, compressive force. And at the bottom, this will be tension forces. Okay, now let's draw this in two-dimensional. So for 2D, if this is our neutral axis, then the stresses would be like this. So you can draw this stress distribution maybe here or maybe at some space. So that depends upon you. Okay, so we have tensile stresses here, tensile forces or tensile stresses, and right here we have compressive forces. Now, what do we observe is that at the neutral axis, the stress at neutral axis is equal is 0, and the maximum occurs at the outermost fiber. So right here on top, it's gonna be compressive, and right here at the bottom, bottommost fiber, that's gonna be the maximum. Let's write here sigma max, and right here we have sigma max. Okay, and recall that the distance from the neutral axis to the outermost fiber, we denote it as C, or sometimes Y if it's just somewhere right here. Okay, and what else? So if this is compressive stress, then this means that the portion right here, we have a compression zone, and right here we have a tension zone. Now the question is it always that the compression is on top and the tension is at the bottom? And the answer is not is no. Why? Because that depends upon the the support conditions and the loading conditions. Like for example, if we have a cantilever beam and we load it in this manner, so you would notice that the bending would be something like this, right? So which one compresses and which one is in tension? Now you would notice that the compression, I mean, let's say this is our neutral axis. That's the uh, I mean that's the neutral axis, and at the bottom right here it shortens. So that means that at the bottom is compression, and at the top is tension. So again, the positioning of tension and compression zones, that depends upon the support conditions and the loading conditions. Okay, and another question is the stress, I mean, is the neutral axis always at the midpoint? And the answer is not, because that depends upon the shape of the cross section. Like for example, if you have a symmetrical shape like this, so the centroid for this composite shape actually lies at the midpoint. Okay, so that is true, but for non-symmetrical shapes such as this, then the centroid is not actually at the midpoint. So it's gonna be somewhere here. So just take note of that. It's not always at the midpoint. Okay, now how do we compute for the stresses? Okay, so how do we compute this stress? And our working equation is this one. So sigma b is just equal to mc all over I. Okay, so again, here's our working equation, and this one is the bending stress, and this one is the internal moments. Okay, take note, this is internal force or internal moments, and usually we take the maximum moment from the moment diagram, and this one is the distance from the neutral axis to the let's say to the point of consideration, to the point of consideration or the outermost fiber, sometimes because that's where the maximum stresses exist, and this one is the moment of inertia. Okay, now for the units, the unit of moment is let's say Newton meter, and the unit of C is meter, and the unit of this one is meter to the fourth, so that simplifies to Newton per meter squared. So this is just gonna be pascals, right? Or its English equivalent in terms of psi or other units. Okay, now we have tensile stresses here, and we have compressive stresses, and the direction is actually is just simply the opposite. And for compressive stresses, that's gonna be negative. We are going to put a negative sign right here. But for tensile, that's the assumption is that it's gonna be positive. All right. Now I guess that's our stress equation, and let's go now for our strain equation. Now, if we consider this this beam segment, so let's say we cut a segment right here, and we'll only consider this portion, then what we'll see is this one. Okay, so we have this beam segment right here, and this is our neutral axis. Okay, and on top there's going to be compression, and at the bottom it's going to be in tension. So in terms of strains or in terms of deformation, the top one is actually is shortening, while the bottom portion is experiencing elongation. Okay, so here's our original, or here's our initial or our reference point, this length right here. Okay, so here's our reference point, the neutral axis, and on top it shortens in terms of it could be in terms of this arc length, or in terms of linear lengths. Okay, later I'll explain that. And right here, at the bottom, the bottommost portion is elongating, so this one is larger as compared to the neutral axis. Okay, so now let's consider, what if we consider a plane or a fiber right here. So it's not the outermost fiber, but rather just some fiber above the neutral axis but below the outermost fiber. And the distance from this neutral axis to that plane under consideration is y. Let's just denote this as y. Now, because this one curves, then there's got to be a center point. Okay, so here's going to be our center point, and the distance from the center point to the neutral axis, that's what we call the radius of curvature. Okay, so that's the radius of curvature, and the angle in between is let's denote this as delta theta. And since this is a delta theta, then the arc length right here, it's gonna be delta s, right? Because from this simple geometry, we know that this relationship, we have this rho, the radius, we have this the angle, and the arc length. So that's the curve distance. And the relationship is actually s is equal to rho theta. However, since we are dealing with a very, very small, or we are dealing with infinitesimal values, this delta theta, actually we want to shrink this down to 0. So that delta s is actually equal to the delta x, the linear distance. Okay, so that simplifies the equation. So that's why right here we have delta x, although I've drawn this in a curve length, but it's just the same because we are dealing with a very small angle. And this length right here, or the linear length, that's let's denote it as delta x. Now recall that in axial stress or in axial strain, we have this equation. The extensional strain is just simply equal to the deformation divided by original length, right? And what is our deformation? It's just simply the delta x prime, that's the final here, the final minus the initial. So that's why delta x prime minus delta x. And this original length is delta x. And if we take this relationship, then we can express delta x prime as rho minus y, because that's the distance from the center to this plane under consideration. So that's just rho minus y. Okay, times delta theta times the angle, and the delta x can also be expressed in terms of rho times delta theta. And therefore, if we substitute the value, we are left to this equation that the extensional strain is just equal to the negative of y divided by rho. And another parameter that's also common is this one. You can express the radius of a curvature in terms of the curvature itself, the Greek letter kappa. So that's just 1/rho. And what that means, if we illustrate that, is if we have, it means since they are in reciprocal to each other, then that means that if we have a small radius, then our curvature would be large because it curves much. And if we have a large radius, then we will have a small curvature. Okay, and in our lecture handouts, there's also uh, this, details regarding the assumptions when deriving these equations, and you can just read that. Now I'm going to move on to the moment curvature equations. Okay, so we still apply the Hooke's law even in the bending stress, and if you apply that, so if you see here, we have the bending stress is equal to the modulus of elasticity times the strain. Alright, let's write it here. So we have the bending stress is equal to the modulus of elasticity times the strain. But what is this bending stress? This is just mc over I, or my over I. Okay, so we can just write my as well. So if we are not referring to the outermost fiber, then we can just write y. Okay, and for this one, E. And this one, for the bending strain, we know that this is y all over rho. Okay, recall that we have a negative right here, but that negative one is actually just means that it's in compression, or it shortens, and if it elongates, then that's going to be positive. Okay, so since we have y in both sides, then we can just cancel this out. So what we're left with is m is equal to ei all over rho. So here's going to be the relationship between the force and the deformation, and this one is in terms of radius of a curvature. Okay, so I guess that's all, and we will do sample problems in the next videos. Alright, so see you in the next video.